Good evening and welcome to the Sleepy Club. This is a gentle place where we learn while slowly drifting towards sleep. Here, calm and thoughtful stories share quiet knowledge and guide the mind into rest without effort or hurry. Before we begin, I would love to know where in the world you are listening from tonight and what time it is for you right now. Whether you are wrapped in blankets as the night grows deeper, or watching the sky soften with the first light of early morning, you are very welcome here. Tonight's story takes us on a slow and curious journey through light itself. We will explore the fastest thing in the universe and the quiet mystery of why it can never move any faster. As you listen, allow your shoulders to relax and your breath to deepen. There's nothing you need to remember and nothing you need to understand perfectly. Simply let the ideas pass by gently, like distant stars drifting across a quiet night sky. If you enjoy these slow and thoughtful journeys, you are always welcome to like this video and subscribe to the Sleepy Club. It helps this calm little space grow and helps others find a peaceful place to rest as well. Now we begin our journey into the quiet and fascinating story of light and the speed that shapes the universe itself. So settle into where you are, let your shoulders soften, close your eyes if that feels right, and allow yourself to drift slowly into a thoughtful wander through the story of light and the quiet mystery of why it is always in such a hurry to arrive. Light is one of those familiar presences we believe we understand, right up until the moment we try to describe it, because it slips so easily into our lives that we forget to question it. You touch a switch and suddenly it is there, spreading gently across the room, revealing the silent judgment in your cat's eyes, warming the glow of your phone screen long after you promised yourself you would put it down. And yet, beneath this everyday intimacy, light asks a deeper question. What is it really? Is it a wave, a particle, something ghost-like, or perhaps a cosmic messenger moving with an unwavering sense of urgency? The simplest answer is yes, and also something more subtle than that. To understand why light has a speed it never escapes, we first need to understand what it is that moves so endlessly through the universe. At the heart of light are photons, tiny packets of energy that form the substance of illumination itself, OTT. You can imagine them as quiet messengers gliding through the vast emptiness of space at the fastest pace the universe allows. These messengers are unusual, not solid like marbles or peas, not resting, not carrying mass, and not obeying the familiar rules we expect from ordinary objects. A photon never pauses, never settles, and never stands still. And just when that seems strange enough, light reveals another layer of its nature. Photons are also waves, though not waves of water or air, but electromagnetic waves, gentle oscillations of electric and magnetic fields, moving together at right angles to one another and to the direction of travel. It is an elegant motion. Two invisible fields weaving through space in perfect balance. A kind of silent dance that needs no stage. Most waves require something to move through. Sound needs air. Water waves need water. Even a friendly wave across a fence needs a neighbor to see it. Light is different. It travels effortlessly through the vacuum of space, crossing vast distances without resistance or rest. This is why the warmth and glow of the sun can reach Earth from more than 90 million miles away, its photons journeying through emptiness without a single pause along the way. And the light that reaches us is only a small portion of a much larger family. Visible light occupies a narrow band within the electromagnetic spectrum, like a few central keys on a piano that stretches endlessly in both directions. On one extreme of this spectrum lie radio waves, long and relaxed vibrations that can span miles to peel. On the other end are gamma rays, sharp and energetic, capable of passing through nearly anything. often born alongside exploding stars and nuclear reactions. Between them lie microwaves, infrared waves, that quietly operate your television remote, ultraviolet light that warms skin into sunburn, and X-rays that peer through bone while somehow never locating missing socks. Despite their differences, every one of these forms of light travels at the same speed in a vacuum, about 299,792,458 meters each second. It is a number so large it feels abstract, almost humorous, as though asking how fast something moves, and receiving the answer everything. To imagine it more gently, if light were a runner, it could circle the entire Earth more than 7 times in a single second. Not bad for something with no legs at all. And yet this speed is not always constant. When light moves through materials like water, glass, or diamond, it slows down, not from fatigue, but from interaction. Each photon brushes against atoms, momentarily delayed as energy is absorbed and released again. It is like walking through a crowded room, still moving forward, but weaving gently between others along the way. This slowing creates refraction, the bending of light as it passes from one material to another, making straws appear bent in water and diamonds shimmer with brilliance. Even here, the mystery deepens. Between each interaction with atoms, photons still move at their usual speed. The overall slowdown comes from the longer path taken, not from hesitation. It is a complex journey, like speed walking across a dance floor filled with enthusiastic uncles at a wedding. Light also carries color, a quiet code written in wavelength. When we see rainbows, prisms, or oil shimmering in a puddle, we are witnessing light separated into its many vibrations. Red stretches long and relaxed, violet vibrates short and energetic, yet all remain photons, all remain waves of the same family. Your eyes contain special cells called cones, each tuned to respond to particular ranges of these wavelengths. Color is not something objects possess, but something your brain constructs. An apple appears red because it reflects certain wavelengths while absorbing others. In this way, color is a gentle interpretation, the mind's best guess, based on which vibrations reach the retina. And beneath all of this is another quiet truth. Light has no rest mass. It does not require energy to move because motion is its only state. If a photon were to stop, it would not pause, it would vanish. It is movement or nothing at all. This is not poetry, it is physics. So here we are, surrounded by massless packets of energy that behave as both waves and particles, traveling at a universal speed, bending, scattering, reflecting, and delivering the experience of sight and color to conscious minds like ours. And this is only the surface. For tonight, let us rest with a single image. Light as a tireless traveler made not of substance but of energy. It never sleeps, never pauses, always tracing the edges of the world. It reveals the stars, the faces we love, the quiet pages of familiar books, and it does all of this while obeying one of the universe's most curious rules, a speed it will never exceed and never fall below. Light is not only what allows us to see, it is how the universe softly whispers its story into our eyes. If you're ready, in the next part we can drift gently backward in time, to an age before satellites and lasers, before precise instruments, to a world lit only by fire and distant stars, where even imagining the speed of light was a quiet act of wonder. It once seemed almost absurd, because for most of human history, people believed light moved instantaneously. It was simply there. You lit a candle, and the room filled with brightness. The sun rose and the world turned gold, with no waiting and no delay. It felt obvious, almost unquestionable, and there seemed little reason to imagine anything else. Even in ancient times, when the Greek philosopher Empedocles suggested that light might have a finite speed, the idea was not taken seriously. Aristotle, whose opinions had a habit of lingering for centuries, believed light was instantaneous, and with that the matter appeared settled and curiosity quietly placed back on the shelf. Then came Galileo, a man who rarely accepted an answer just because it came from someone important. He preferred to test ideas by touching them, dropping them from towers, and turning telescopes toward unfamiliar moons. Around the year 1638, he attempted what may be the most charmingly optimistic experiment ever designed to measure the speed of light. The plan was simple in spirit. Galileo and his assistant stood on hilltops about a mile apart, each holding a lantern that could be covered and uncovered. Galileo would uncover his lantern, and the moment his assistant saw the flash, he would uncover his own in reply. Galileo would then measure the time between sending the signal and seeing the return light. Even in ideal conditions, this experiment asked a great deal. Human reaction time alone lasts about a quarter of a second, while light takes less than a 10,000th of a second to travel a mile. It was like trying to measure the speed of a bullet with a sundial to all shows. Unsurprisingly, Galileo concluded that if light had a finite speed, it was far too fast for him to measure, which was true. But the important thing was that the question had finally been asked. A few decades later, the answer began to emerge quietly through the work of a Danish astronomer named Ole Romer. In 1676, he was studying something very distant, the moons of Jupiter. One of these moons, Io, circles the gas giant with remarkable regularity, like a piece of cosmic clockwork. By carefully observing when Io disappeared behind Jupiter and when it reappeared, Ruma noticed something subtle but persistent. The timing was not always the same. Sometimes the moon appeared slightly late, other times a little early. At first this seemed like error or coincidence, but then came a simple and brilliant thought. What if Io was perfectly consistent, and the variation came from us? When Earth was farther from Jupiter, the light from Io had farther to travel. With that realization, the idea of light having a measurable speed took solid scientific form. From these delays, Romer estimated that light took about 22 minutes to cross the diameter of Earth's orbit, a distance we now know is roughly 186 million miles. The estimate was not perfect, but it was extraordinary for its time. It showed that light takes time to travel, not much, but enough to matter. In the early 1800s, a physicist named Hippolyte Fizeau decided to try a more earthly approach. His experiment used a beam of light, a rotating toothed wheel, and a mirror placed several miles away. Light passed through a gap in the wheel, traveled to the mirror, and reflected back. When the wheel turned slowly, the returning light slipped through the same gap and could be seen. When the wheel spun faster, the returning beam struck a tooth and vanished. By finding the speed at which the light was just blocked, Fizeau calculated how long the light took to make the round trip. From this he estimated the speed of light at about 193,000 miles per second, remarkably close to the modern value given the tools of his time. Soon after, Léon Foucault refined the method using rotating mirrors instead of toothed wheels, increasing the precision even further. He demonstrated not only that light has a finite speed, but that it travels more slowly in water than in air. This was a vital clue, showing that light interacts with materials in ways that affect how fast it moves. Then came Albert Michelson, whose name would become inseparable from the speed of light itself. In the late 1800s, he perfected these techniques using long tunnels, exquisitely aligned mirrors, and extraordinarily precise timing. His measurements stunned the scientific world and earned him the Nobel Prize in Physics in 1907, making him the first American to receive the honor Dr. A fitting reward for someone who spent his life chasing beams of light through space and reflection. Today, our tools are even more refined. Lasers, atomic clocks, satellites quietly circling Earth. We no longer measure the speed of light in the traditional sense. Since 1983, the meter itself has been defined by it as the distance light travels in one divided by 299,790,2,458 of a second. We have turned the equation around, using light as the ruler by which everything else is measured. And yet it all began with lanterns on hilltops, careful watching of distant moons, spinning wheels, and a simple wonder about whether the universe might be slower than it appears. The speed of light is more than a number. It is a story of curious minds, imperfect tools, and patient persistence unfolding across centuries. A story told from mountaintops, observatories, and silent orbits far from Earth. It is proof that even the fastest thing in the universe could not outrun human curiosity. And now that we have met our tireless photon companion and followed the long path to measure its pace, another question quietly waits. Why does light not go faster? Why does this massless bundle of energy obey a cosmic speed limit at all? To explore that question, we take a gentle step into one of the most elegant and mind-bending chapters of physics: electromagnetism. Here we meet James Clerk Maxwell. In the 1860s, Maxwell gathered everything known about electricity and magnetism, the sparks and rods of Benjamin Franklin, the coils and fields of Michael Faraday, and shaped them into four graceful mathematical relationships. These became known as Maxwell's equations. They describe how electric and magnetic fields move, change, and create one another. When Maxwell combined them, he uncovered something astonishing. The equations predicted waves born from oscillating electric and magnetic fields, waves that would always travel at a specific speed. When he calculated that speed using known constants, the number emerged quietly and unmistakably: 299,792,458 meters per second. The speed of light itself. Maxwell was stunned because he had uncovered a number, a fundamental speed hidden deep inside the laws of electricity and magnetism. And the astonishing part was that this number matched the best measurements of the speed of light available at the time. This was not coincidence. It was revelation. Light, Maxwell realized, was an electromagnetic wave, a self-sustaining ripple of electric and magnetic energy, moving through empty space at a speed dictated not by chance, but by the very structure of the universe itself. Let that settle gently. The speed of light is not a habit or a preference. It is written into the equations that describe reality. The universe did not spin a dial and land on a convenient number. If electric and magnetic fields exist, and they do, then light must move at this speed. Anything faster or slower would tear apart the rules that hold the cosmos together. That explains why light moves as fast as it does. But another question quietly follows. Why can nothing move faster? In everyday life, speed feels flexible. A car can go a little faster if you press the pedal. A runner can sprint if they try harder. But light has no such option. There is no upgrade, No shortcut, no pushing past the limit. To understand why, we gently invite a familiar mind into the story. Albert Einstein taught it. In 1905, Einstein introduced his special theory of relativity, and with it, the universe shifted its posture. One of its core ideas was simple to say and astonishing to accept. The speed of light in a vacuum is the same for all observers, no matter how fast they are moving. Imagine riding a train that moves at nearly the speed of light. You switch on a flashlight. Common sense suggests the beam should move faster for someone standing still outside the train, but it does not. You and the observer both measure the light at exactly 299,792,458 meters per second. Not more, not less. To make this possible, reality itself adjusts. Time slows down, lengths shrink, mass increases. The universe reshapes how it ticks and stretches so that light always keeps its pace. If you tried to accelerate yourself closer and closer to light speed, you would feel this resistance grow. Each small increase in speed would demand more energy than the last. As you approached the speed of light, your mass would rise without bound, requiring infinite energy to go any faster. Infinite energy is not available, even in the grandest imagination, and so you can approach the light, but never arrive. You can chase it, but you will never catch it. This is why the speed of light is more than just a number. It is the cosmic speed limit. Nothing with mass, nothing that carries information or energy, can cross it. It is a boundary built into space-time itself, and there is a quiet kindness in this rule. If light had no limit, cause and effect would unravel. Effects could arrive before causes. Information could travel backward in time. Logic would dissolve into paradox. The universe avoids this chaos by holding firm to its gentle rule. Light goes this fast, and no faster. So when you watch a sunset, or look up at stars whose light has traveled for years to reach you, remember that those beams followed a rule older than planets, a rule carved into the bones of physics, a rule that says this far, no farther. It is a limit, but it is also a gift. It keeps time flowing forward. It keeps reality understandable. Light does not go faster because it cannot, not from weakness or laziness, but because it is already perfect in its motion, bound to a speed that gives the universe structure, stability, and beauty. Einstein had a rare talent for turning reality inside out and making it feel inevitable, as if the universe had been whispering truths for ages, and he was simply listening carefully. When he presented special relativity, he did not gently adjust physics. He rewrote its foundations. At its heart was a bold declaration. The speed of light is constant, everywhere, for everyone, always. Even as you drift towards sleep, this idea quietly breaks the everyday rules of motion. And time I go early. Picture yourself floating peacefully through space, holding a flashlight. You turn it on, and the beam flows forward at its familiar speed. Now imagine another traveler passing you at half the speed of light. To them you are rushing by, and yet when they measure that same beam of light, they find the same number. The speed does not add, subtract, or bend. It simply is. In daily life, speeds stack together. Walking on a moving walkway makes you faster relative to the ground. But light refuses this logic. Everything else must adjust instead. Time stretches. Space contracts. Moments change their length. Distances change their size. all to preserve that one constant speed. One gentle consequence is time dilation. The faster you move, the slower time flows for you compared to someone at rest, not as a feeling, but as a measurable fact. A traveler moving near light speed experiences fewer moments than those left behind. This is not imagination. We observe it in particles called muons, created high in Earth's atmosphere. Normally, they decay almost instantly, but when moving near light speed, their internal clocks slow, allowing them to reach the ground before fading away. Time itself stretches to accommodate their motion. Another consequence is length contraction, where distances along the direction of motion shrink for fast-moving travelers. Space subtly rearranges itself. These effects may feel strange, but together they protect the universe's most important rule. The speed of light remains unchanged, and as you rest with that thought, allow it to feel less like a puzzle and more like a rhythm, a steady pace woven into the cosmos, a quiet agreement between space, time, and energy, one that allows the universe to remain calm, connected, and gently understandable, even as you drift deeper into rest. This is the quiet twin of time dilation, length contraction, and it tells us that when you move at very high speeds, objects along the direction of motion become shorter, not as a trick of perspective, not as an optical illusion, but as a real, physical change. A spaceship traveling close to the speed of light would truly measure shorter from nose to tail along its path. There is no need to worry about folding into an uncomfortable shape, because this effect only becomes meaningful at speeds brushing up against light itself. In everyday motion, cars, airplanes, even the most determined joggers experience a contraction so tiny it might as well not exist. But near light speed, the universe softens, distances yield, and space itself becomes gently squishy dynamite. Alongside this comes another strange and beautiful idea, the relativity of simultaneity. The name may feel like a tongue twister, but the idea is surprisingly graceful. It means that two events which appear to happen at the same time for one observer may not happen at the same time for another observer who is moving differently. Picture a fast-moving train. A light flashes at the exact center of the train. For a passenger inside, the light reaches the front and back at the same moment. For someone standing still on the platform, the light reaches the back first, because the front of the train is moving away from the flash. Both perspectives are correct. Time and space are no longer universal backdrops. They are flexible, local, and relative. All of this strangeness, time stretching, distances shrinking, simultaneity gently unraveling, exists for one reason. It protects the constancy of the speed of light. It is as if the universe looked at this single number and quietly decided that everything else could bend. But this must remain unbroken. It resembles a cosmic contract. In exchange for letting light keep its pace, the universe agrees to reshape space and time around it. This balance preserves causality, the simple and comforting idea that causes come before effects. Here is a calming thought to rest with. This cosmic speed limit is what protects our sense of before and after. Because light travels at a finite speed, information does too. That means you cannot see an event before it happens. You cannot receive a message from the future or send one into the past. The limit keeps reality orderly, predictable, and quietly sane. Without it, effects could arrive before causes. Messages could be received before they were sent. Paradoxes would accumulate endlessly, like laundry that never quite gets folded. Instead, the universe gently declines such confusion and insists on order. This is where Einstein's work shines most clearly. He did not merely describe the speed of light as a limit, he revealed it as a cornerstone of reality, a scaffold holding up space and time themselves. Today, this insight quietly supports everyday life. GPS satellites rely on these principles so your phone knows where you are, instead of placing you in the middle of an ocean. Particle accelerators depend on them to guide subatomic particles racing near light speed. Astronomers use them to translate faint signals from distant galaxies into meaningful stories. All of it rests on this single constant truth. Light has a maximum speed, and that speed is the same for everyone. So when you notice a sunbeam drifting across your room, or a lighthouse blinking patiently in the dark, remember what that light represents. Not just warmth, not just energy, but the delicate geometry of space-time itself, a quiet agreement written into reality. No matter how fast you move or how far you wander, light will always arrive at the same pace, steady, reliable, and perfectly on time. So far we have explored what light is, how humans learn to measure its speed, and why the universe insists on giving it such a precise and unbreakable limit. So, consonantly, now we can gently pull back and see what this cosmic speed limit does to reality as a whole. Once you accept that light cannot move any faster than it already does, the consequences reach far and wide, and many of them are quietly beautiful. Begin with time itself, not the ticking clock on a wall, but the deeper time that connects events, memories, and cause and effect. The speed of light gives time its structure. It draws boundaries around what can influence what. It tells the universe that connections may only form if there is time for light to travel between them. This idea is captured in what physicists call the light cone. Imagine standing in an open field and striking a match. Light spreads outward in all directions. The region of space that can ever be affected by that spark is limited by how far light can travel from that moment onward. Someone standing very far away, perhaps 100 light years distant, will not know the match was lit until 100 years have passed. Now, reverse the view. 20. The only events that can influence your present moment are those whose light has already had time to reach you. This is your past light cone. Everything that could possibly have shaped what you experience now. The light cone is not just a diagram. It is the border between possible and impossible. Events outside it are not merely distant. They are distant in time. No signal, no sound, no whisper from them can reach you yet. Until the light arrives, they may as well not exist for you. This simple rule reshapes how we understand the universe. There is no instant communication. There is no single universal now. Every moment is local. Every present depends on where you are. The speed of light quietly enforces this consistency. Consider the night sky. When you look at the stars, you are not seeing them as they are. You are seeing them as they were. Light from the nearest star system, Alpha Centauri, takes more than 4 years to reach Earth. If something dramatic happened there last week, it will remain unknown to us for years to come. And that is our cosmic neighborhood. Look farther. The light from the Andromeda galaxy takes more than 2 million years to arrive. You see it as it was when early humans were only beginning to shape tools. Look even deeper, and the light you see left its galaxies billions of years ago, before our sun was born. And yet it feels present. The stars shine. The galaxies glow. History arrives softly, carried by light moving at its patient pace. This delay allows astronomers to become quiet travelers through time. When they look into deep space, they are also looking into the past. God, every telescope becomes a kind of time machine. All of this is possible because light does not move instantly. Its limit opens a window into history. There is also elegance in how this limit preserves logic. You cannot influence something unless there is time for a signal to arrive. This is not a restriction meant to frustrate. It is a safeguard. Without it, causality would collapse. Faster than light signals could send messages backward in time. You could warn your past self not to make a certain choice, and if you succeeded, you would never need to send the warning at all. The paradox would knot itself endlessly. Instead, the universe keeps things gentle and sensible. Light moves at its chosen pace. Causes come before effects. Time flows forward. And within that structure, the cosmos remains understandable, stable, and quietly beautiful, allowing you to rest, knowing that even at nearly 300,000 kilometers per second, light is moving exactly as fast as it needs to. That is exactly the kind of logical loop that keeps theoretical physicists awake at night, and not in a pleasant way. With the speed of light standing firm as a limit, those loops never form. You cannot outrun your own consequences. Events unfold in order. The past remains behind you, and the future stays ahead. This is not merely the flow of time. It is the structure of time itself, and it reaches far beyond distant galaxies or imaginary machines. It is quietly woven into everyday life. Think about communication. When you make a phone call or send a message, light speed rarely crosses your mind. Yet when you speak to someone on the other side of the planet, there is a tiny delay, almost imperceptible but real. Your words travel as electromagnetic waves, bouncing through satellites and racing along fiber optic cables. They move at or near the speed of light, and Earth is wide enough that even light needs a moment to cross it. Now think farther out. When Mission Control sends a signal to a rover on Mars, that message takes time. Depending on where Earth and Mars sit in their orbits, the delay can be anywhere from 4 to 20 minutes. If the rover encounters trouble, scientists will not know right away. There is no instant response, no real-time control. The rover must make its own decisions. Out there, the speed of light gently says, "You are on your own." Even your favorite streaming service obeys this rule. Every pixel, every frame of a late-night documentary travels as pulses of light through cables and switches. The delay is small, but it exists, and rather than feeling like a restriction, it creates a kind of harmony. The speed of light gives us a universe where causes come before effects, where the past is fixed and the future waits patiently. It gives structure to space and time. It turns an endless void into a tapestry of ordered events. It may seem strange that the fastest thing in the universe is also what limits how quickly we can know something happened. But those tiny delays give us distance, perspective, and breathing room. They make the universe understandable, and perhaps they even give us a little space to rest. Now imagine for a moment that you are not the kind of being who accepts limits easily. You hear about this cosmic speed rule etched into physics, and your first instinct is to wonder what happens if we ignore it. Could anything ever go faster than light? Humans have always pushed boundaries. We broke the sound barrier. We sent machines to Mars. We learned how to split atoms. Surely there must be a shortcut. Enter one. of the more curious ideas from the depths of theoretical physics, tachyons. These hypothetical particles appear in certain equations, and come with a startling trait. They can only move faster than light. In fact, they cannot slow down enough to reach light speed at all. It sounds thrilling, like a particle that casually ignores the universe's rules. There is just one issue. No one has ever observed a tachyon. Not in laboratories, not in space, not hidden between equations. They remain rumors without witnesses. Even if tachyons did exist, they would bring trouble with them. If they could carry information, they would allow messages to be sent into the past. Causality would fracture, paradoxes would multiply. Timelines would tangle. For this reason, most physicists treat tachyons as interesting but unlikely, entertaining to imagine, but probably not real. What about something we know exists? Quantum. One of the strangest features of reality. When two particles become entangled, measuring one appears to instantly affect the other, no matter how far apart they are. Measure one on Earth and its partner across the galaxy responds in perfect correlation. It feels like cheating. It feels faster than light. But there is a quiet catch. While entanglement correlations appear instant, they cannot transmit useful information. You cannot control the outcome of the measurement. There is no way to send a message. It is like two distant coins that always land the same way, but neither coin can choose heads or tails. Einstein disliked this deeply and called it spooky action at a distance. Experiments have since confirmed entanglement is real, but still obedient. The universe remains strange but respectful of its speed limit. Then there is Cherenkov radiation, a soft blue glow that appears when a charged particle moves through material faster than light can move through that same material. Light slows down in water, glass, and plastic because it interacts with atoms. If a particle outruns that slowed light, it creates a shock wave of light, similar to a sonic boom. This is the eerie glow seen in underwater nuclear reactors. Nothing here breaks the universal rule. Light in a vacuum still holds the crown. The law is not broken, only locally bent. And of course, there is the dream of bending space itself. Instead of moving through space faster than light, what if space could move? In the 1990s, physicist Miguel Alcubierre proposed a model where space contracts in front of a ship and expands behind it. The ship would ride a wave of space-time, never locally exceeding light speed, yet arriving sooner than light, traveling normally. It is a clever idea, but it demands exotic matter with negative energy density, something we have never observed. The energy requirements are enormous. Some estimates suggest you would need the mass energy of a planet just to move something the size of a grapefruit. For now, warp drives remain storytellers' tools rather than engineers' plans. Wormholes offer another tempting vision. Tunnels through space-time, connecting distant regions. Particles, mathematical shortcuts. The equations allow them. Reality resists them. Stability issues, exotic matter, and paradoxes pile up quickly. Even if one could exist, it would not truly beat light speed. You would simply take a shorter path. Light would still win the race. So after all these possibilities, where does that leave us, Tutti? It leaves us with a universe that invites imagination, but enforces coherence. A cosmos that allows wonder without unraveling itself. Light sets the pace. Everything else follows. And within that steady rhythm, reality remains navigable, meaningful, and quietly kind to minds like ours, as we drift gently toward rest. Despite all the clever ideas and tempting exceptions, nothing with mass or usable information has ever been observed traveling faster than light. Each time it seems a loophole might exist, the universe calmly steps forward and closes it, not with drama, but with quiet certainty and equations that leave little room for argument. And perhaps that is not a limitation to resent. What first appears as a locked door at edge of possibility is more like a safety rail, gently preventing reality from tumbling into paradox, chaos, and tangled timelines. The speed of light gives the universe structure. It gives order. It offers a kind of cosmic serenity, the reassurance that no matter how strange things become, there are still boundaries that even the universe respects. So if you ever catch yourself wishing you could leap across the stars or send a message to your past self about tomorrow's weather, take comfort in this, PTO. Light itself. Swift, silent, and steady, is already moving as fast as anything possibly can. It is already leading the way, and perhaps that is enough. By now, a pattern may be gently revealing itself. The speed of light is not an arbitrary number plucked from nowhere. It is a foundation stone, woven deeply into the architecture of reality, and it may be telling us something even more profound. What if that almost poetic number, 299,792,458 meters per second, is not just a speed limit, but a key to understanding space, time, and existence itself? Let us take a calm step into a more philosophical corner of physics. No need to worry. This path remains soft and welcoming. One of the most intriguing ideas in modern thought is that the speed of light is not merely how fast photons move, but a kind of conversion factor, a bridge between space and time. A bridge between space and time. This number, often called c, allows us to translate distance into duration and duration back into distance. The universe is built-in translator. You may recognize it from Einstein's famous relationship between energy and mass, where the speed of light acts as the bridge that tells us how much energy is hidden within matter. But c appears everywhere in relativity. It shapes equations that describe time slowing down, length shrinking, and space-time curving under gravity. Its constant presence is not coincidence. It is a signal that this number is more than a speed. It is a kind of universal glue. Imagine the universe as a vast woven fabric, not one thread of space and another of time, but a single seamless material, space-time. In Einstein's view, space and time are not separate stages. They are intertwined, flexible, and responsive. When you move through space, you also move through time. When gravity pulls, it bends both together. Here's where the speed of light quietly enters the scene. It is the exchange rate between space and time. Like currency conversion, but instead of money, it trades meters for seconds. This is why distances can be measured in light years. A light year is not time. It is distance per year. It is how far light travels in a year. The ease with which we describe distance using time reveals how deeply the two are connected. So when we say nothing can travel faster than light, we are also saying nothing can disrupt the relationship between space and time. The speed of light defines that relationship. It is the stitching that holds the quilt of reality together. There is something deeply calming in that idea. No matter where you are in the universe, no matter how fast you move, this number remains the same. It is a constant that keeps equations balanced, preserves cause before effect, and allows physics to behave even in the intense gravity near black holes or the glowing hearts of galaxies. Physicists take this so seriously that in many theoretical frameworks, they no longer treat the speed of light as a speed at all. They simply set it equal to 1, not out of laziness but elegance. With c set to 1, space and time can be measured using the same units. The equations simplify. The universe seems to tidy itself. This leads to an even more curious thought. Perhaps the universe is not built for light to move through it. Perhaps it is built around the speed of light itself. Consider this. From the perspective of light, time does not pass. For a photon, the moment it is emitted and the moment it is absorbed occur at the same instant. There is no ticking clock within a beam of light. Time simply does not flow for it. This follows naturally from relativity. As speed increases, time slows. At the speed of light, time stops entirely. Light exists only in motion. It can never rest. And in that way, light does not merely travel through the universe. It helps define the universe as it goes. The speed of light is not something photons choose. It is something the universe insists upon. Even our most basic units of measurement now revolve around it. Since 1983, the meter has been defined by the distance light travels in a specific fraction of a second. We have made light a ruler by which all rulers are judged. And perhaps that is the most grounding realization of all. In a universe filled with mystery, uncertainty, and vastness, something remains beautifully fixed. The speed of light is a constant we can build reality upon, because we quite literally do. So the next time you notice the flicker of a candle, or the soft glow of starlight resting on your wall, remember what you are seeing. Not just illumination, but a cosmic law in motion. A message written into the geometry of space-time. A reminder that while the universe is immense and strange, it is also quietly consistent. Light does not merely brighten the world, it sets the rhythm of the cosmos. And perhaps on a quiet night, as photons from distant stars drift gently down to meet you, you can imagine the universe whispering in its own language, steady and calm, at exactly 292,792,492,400 niters per second meters per second. By now, we have seen that the speed of light is not a footnote in a textbook. It is the pulse of the cosmos, the stitch in the fabric of space and time. Oh, the steady metronome that keeps reality in rhythm. And here's something quietly surprising. This cosmic constant is not only out there between galaxies, it is woven into your everyday life as well. Even if you have never piloted a spacecraft or guided particles around a collider, you are still living inside a world shaped and orchestrated by the speed of light. Let us begin with something very familiar. Your phone, the small device you may be listening to this through right now. Every time you tap a screen, stream a video, or send a sleepy emoji drifting toward a friend, you are quietly borrowing the power of light. More precisely, you are using light as it races through fiber optic cables. These slender threads of glass or plastic form the hidden backbone of the internet. They stretch beneath oceans and across continents, weaving a global web that carries information at nearly the speed of light. When a web page loads, it is not waiting for a distant machine to think. It is waiting for tiny pulses of light, brief flashes encoding ones and zeros, to travel through cables, pass through routers, and arrive gently at your screen. On light in fiber moves a little slower than in a vacuum, about 2/3 as fast, but even so, it still travels at hundreds of thousands of kilometers per second. That is how cat videos, weather forecasts, and bedtime playlists reach you with hardly a pause at all. Those same cables do more than carry data. One of the technologies most deeply dependent on the speed of light is the global positioning system. When you use GPS to find your way to a nearby bakery, your device listens to signals from at least 4 satellites orbiting Earth. Each satellite sends a timestamp precise down to billionths of a second. Your receiver compares when those signals arrive and uses the differences to calculate where you are. It is like asking several friends how far away they are, and then gently triangulating your position. Here comes the quiet marvel. For this to work, the system must account for both special and general relativity. The satellites move quickly relative to Earth, causing their clocks to tick a little slower due to special relativity. At the same time, they sit higher in Earth's gravitational field, which makes their clocks tick a little faster due to general relativity. Without correcting for both effects, your GPS location would drift by several kilometers every single day. Thanks to Einstein's insights and the unwavering consistency of light speed, your device can guide you turn by turn toward the croissant you have been imagining. Now, let us drift closer still, all the way to your eyes. Vision itself is built upon the behavior of light. When you look at the world, you are receiving photons that have bounced from objects into your eyes. These photons pass through the cornea and lens, focus onto the retina, and trigger chemical changes in cells called rods and cones. Your brain transforms these signals into the rich images of trees, sunsets, and quietly judgmental houseplants. Depth and motion depend on tiny differences in the arrival time of light to each eye. Differences so small, they feel like magic. Light bending plays its part as well. Refraction, the slowing and redirecting of light as it enters new materials, is why a straw appears bent in water, and why heat shimmers above a road. It is also the principle behind eyeglasses, microscopes, telescopes, and camera lenses. Every photograph, every page read through lenses, depends on our understanding of how light travels and bends. Even your microwave hums with the influence of light. Microwaves are simply a lower frequency form of electromagnetic radiation. Inside the oven, they bounce and interact with water molecules in food, making them jiggle and warm. Without this understanding of the electromagnetic spectrum, reheating leftovers would be a far less elegant affair. Step gently into telecommunications. Radio stations are light as well, just stretched into longer wavelength. They travel at the same speed in a vacuum and carry music to your car as you move through the world. Television signals, Wi-Fi connections, Bluetooth links, all are electromagnetic waves guided by the same rules that govern starlight and lasers. Medicine also rests quietly on these principles. ACE are high-frequency electromagnetic waves that pass through soft tissue and are absorbed by denser bone, creating those ghostly images of skeletons. Many machines rely on electromagnetic fields to map the body in astonishing detail. But in countless ways, light and its extended family work behind the scenes of modern life. Everything we know about the universe beyond our solar system has arrived on beams of light. Telescopes like Hubble capture photons that have traveled for billions of years across empty space. These ancient travelers carry stories about galaxies, nebulae, black holes, and the early universe. By studying their color and spectrum, scientists learn how fast galaxies are moving, whether planets pass before distant stars, and even detect faint echoes of the Big Bang itself. Whether a photon reflects off your coffee mug or journeys from a galaxy 13 billion years away, it obeys the same rule. It moves with the same unwavering speed. So when you open an app or gaze at the moon, Remember what is unfolding. A graceful dance of photons, electromagnetic fields, and universal constants. Light racing through and around your world at 299,792,458 meters per second. Light is not only a cosmic phenomenon, it rests in your pocket, flows through your home, and shapes your vision. It is the quiet engine of the everyday. Now take a slow breath and imagine a single beam of light drifting through empty space. No planets, no stars, no gravity tugging at it. Just one solitary photon gliding through the vacuum. Never speeding up, never slowing down. It has no mass, no rest, and no need for fuel. It exists only in motion, traveling at the only speed it knows. This image is more than poetic. It offers a glimpse into the fabric of reality itself, Dada. That simple beam of light is not just moving. It is participating in the great cosmic symphony, a dance of energy, information, and time that shapes everything we know. And here we arrive at one of the most awe-inspiring legacies of light, the cosmic microwave background. This is the oldest light in the universe. It has been traveling quietly for nearly 14 billion years. It fills space with a faint, even glow, gently bathing everything it touches. This is not light from stars or galaxies. It is the cooled and softened remnant of the moment the universe first became transparent, about 380,000 years after the Big Bang, when everything had cooled enough for atoms to form and for photons to finally roam freely. Before that moment, the universe was thick and fog-like, hot and chaotic, a place where light could not travel without constant collisions. But once neutral hydrogen appeared, the fog lifted, light was released, and it moved outward in every direction, beginning a journey that continues even now. That ancient radiation has since been stretched by the expansion of the cosmos into gentle microwave whispers tour. When scientists measure the cosmic microwave background, they are catching photons that have been traveling since the dawn of time. These particles of light have never rested. They have crossed the universe only to arrive softly in a detector and quietly tell us what the universe was like back then. This is not just history, it is cosmic archaeology, and the story does not end in the distant past. Light does not only tell us where we have been, it binds together everything we are experiencing right now, from the way stars shine to the way atoms behave. Light is a silent participant in every process around us. Consider photosynthesis. It is the engine behind nearly all life on Earth, and it begins when sunlight touches a leaf. Photons strike chlorophyll molecules, exciting electrons and setting off a cascade of reactions that store energy in chemical bonds. Plants grow using that energy. Animals eat the plants, or eat the animals that eat the plant's diet, and the chain of life continues. Without light, there is no photosynthesis. Without photosynthesis, there are no plants. And without plants, life as we know it quietly fades. In a very real sense, every meal you have ever eaten began with a photon from the sun. Light also shapes us more directly. The human circadian rhythm, the internal clock that guides sleep and wakefulness, is deeply influenced by light. Morning light tells the brain to slow the production of melatonin, the hormone that brings sleep by yacht. As evening arrives and light fades, melatonin rises again, gently guiding the body toward rest. Even now, as you listen and breathe more slowly, your body is sensing the light around you, adjusting its rhythms, sensing itself to the quiet cues of the world. Perhaps the most profound role of light is connection, Tadai. Light connects moments to one another. It carries information. Every time you see something, across a room or across the sky, you are receiving messages encoded in waves and translated by your mind. Light is the language of the universe, and like any language, it has many dialects. Some wavelengths tell stories about the chemical makeup of distant galaxies. Others warn us of gamma-ray bursts, the most energetic explosions known. Some carry the warmth of infrared light from newborn stars dodged. Others paint rainbows across oil slicks and soap bubbles, revealing hidden patterns of interference and refraction. This diversity is what makes light so powerful. It does not only show us what exists, it explains how things work. A beam split by a prism reveals that white light is a harmony of colors. Light from a supernova carries the signatures of heavy elements forged in the violent heart of a dying star. And over time, we have learned to listen more carefully. Radio telescopes here, the quiet whispers of hydrogen clouds. X-ray observatories reveal the skeletal structure of galaxy clusters. Infrared instruments peer through dust to watch stars being born. And gravitational wave detectors listen not to light, but to ripples in space-time itself. Another cosmic messenger complementing what photons have long been telling us. Together, these signals reveal a universe that is not cold or silent, but rich with stories, a universe filled with communication and light. And they remind us that we are not separate observers standing outside it. We are immersed in it, shaped by it, part of it. The atoms in your body were forged in stars that shone billions of years ago. Their light crossed vast distances, touched clouds of gas, and helped seed new solar systems. That same process created the carbon in your cells, the calcium in your bones, and the iron in your blood. You are quite literally made of star matter, carried forward through the universe by light. And so this restless traveler, this photon with no mass, no clock, and no home, does more than move. It connects the ancient past to the present moment. It links atoms to galaxies. It allows eyes to see and minds to understand. In a universe filled with mystery, light remains a constant companion, not only fast and fundamental, but familiar. It is the quiet presence that turns space into story and fills darkness with meaning. It whispers across the vastness and gently says it is still here. So tonight, as you settle in and let your thoughts drift among the stars, remember that even in silence and even in darkness, light is always on its way. And now we find ourselves gently returning to where we began. We set out with a simple question. Why does light have a speed limit? Along the way we wandered through photons and electromagnetic waves. We listened to the universe speak through ancient radiation. We watched time bend and space stretch. We followed light through cables and galaxies, through your phone, your eyes, and the quiet glow of the cosmic microwave background. And the answer is as elegant as it is profound. Light travels as it does because the universe is built to let it and to be shaped by it. Its speed is not just fast, it is fundamental, a cosmic rule that holds everything together, from the rhythm of atoms to the expansion of galaxies. It cannot be outrun or broken, and perhaps that is a gift. The speed of light gives us order, it gives us time, it gives us understanding, it gives us stories in sunsets and the soft warmth of starlight on a quiet night. Maybe it does not need to be faster. Maybe it is already perfect exactly as it is. And as we bring this calm journey to a close, let me gently ask you once more, where in the world are you listening from tonight? And what time is it where you are? Are you resting beneath a dark sky filled with stars, or sitting somewhere far away where morning light is just beginning to rise? Wherever you are, and whenever this finds you, thank you for spending this time with me. If this story helped you slow down, or sparked a quiet sense of wonder, a like or a subscription helps others find their way to this calm corner of curiosity. And if it kept you awake just a little longer, perhaps you learned something interesting while waiting for sleep to arrive. Until next time, rest well, and may your dreams move gently, calmly, at just the right speed.